So we're very much delighted to have Shannon Harris from Virginia Commonwealth University. And I've known Shannon for, I guess, exactly 8 years. We met at an Informs conference in Chicago, the Informs Healthcare Conference. And she's been a great friend. And this is her first time at Cornell. And she's going to tell us a little bit about machine learning and appointment scheduling. And what's very interesting is that this work has won a number of awards and was also featured in Forbes magazine. So we're very much delighted to have her today. And Jake will fix the screen.
Oh.
Perfect.
Perfect. Thank you. Thank you so much, and thank you for the introduction, Jamal. Thank you so much for having me. Can you guys hear me very well? Okay, perfect. So this is work that started with Michele Samarani and I. Samarani is at Santa Clara University. So Michele and I have been working together, just trying to sort of make our way in the research world and try to find sort of an innovative way to discuss healthcare scheduling. When Michele went to Santa Clara University, he met Michael Santoro, who is an ethicist. And Michael looked over some of the work that we had done and said, you know, there are components here in terms of the algorithms that you're building. And so is there algorithmic bias in healthcare scheduling? And sort of that question sort of took Michele off onto this research stream. So we partnered with him, Michael Santoro, and then someone else at Santa Clara University, Haibing Liu. And I think what really makes this project work is that we also partnered with Linda Goler-Blount, who is the CEO of the Black Women's Health Imperative. So Michele and I kind of brought the desire and sort of the ability to talk about the concepts of data mining and machine learning. But what Linda really did is she helped us focus it from a social standpoint and understanding sort of what we were doing, how it could actually affect people. And so she was able to sort of write some of the paper with a very fiery passion. And we were able to say, okay, let's use some of those words and try to find a mathematical way to back them up so we can sort of have this paper, this research that can really make a difference. So I really just wanted to point out the research team because I think it was very important to the success of this work that we had a very diverse research stream, research group with people from various backgrounds. Okay, so for people who are not familiar with scheduling in general, I will start out with discussing sort of the basics of scheduling and sort of what we think of when we're talking about building a scheduling algorithm and sort of the schedule structure. So when we're talking about the concept of outpatient clinic settings, there are patients who interact with the system. They schedule appointments, but they also may not show up for their appointments. When they don't show up for their appointments, it can be very disruptive to the clinic because the doctor is idle, or potentially the way that the clinic schedules, because people may not show up, results in there being extra waiting and overtime. In the data set that we have for the clinic that we got our data from, the show rate is about 74%. And that's actually pretty low. So about 26% of people don't show up for their appointments. So in order to make sure that the doctor is able to not be idle during the day, they need to be able to mitigate the negative effect of no-shows. Depending on the type of clinic you have, you could potentially charge patients for not showing up. Sometimes it's not possible. You're not able to charge patients for not showing up. One thing in literature that we have found in order to mitigate no-shows is to call people and remind them. Part of the work that I did prior to this was with data based from the Veterans Affairs, and they did this huge survey project where they asked patients, okay, you had an appointment, you didn't show up, why not? And the number one reason was, I forgot. And so this concept of reminder calls says, hey, you know, maybe we'll just remind people that they have an appointment and then they'll show up. In literature and sometimes in practice, what clinics do is that they overbook patients. They overbook patients in that they schedule more than one patient in the same appointment slot, hoping that at least one of them comes so the doctor is able to serve someone. So let's talk about sort of the basic concepts of overbooking and what can happen when we overbook. But in the beginning, when we were talking about scheduling, I'll try to move this off to the side a little bit more. We just scheduled based upon the population show rate. We weren't using any sort of data mining or machine learning algorithms to generate patient no-show probability, but we understood the population show rate of our clinic, and we just used that to schedule appointments. If a clinic doesn't overbook, we have a situation such as this, where there is a single patient in each slot. If some of these patients don't show up, then this can be a negative thing because there's 2 empty slots during the day. So let's say another person had called in and they were denied appointment because the schedule was full, but in actuality, there's empty space in the schedule, so this is bad. So let's say the clinic says, all right, let's overbook. I will schedule 2 patients for the first slot, 1 for the second, 1 for the third, and 2 for the fourth and the fifth, and so on. Now, this could work well. Let's say we come up with this sort of outcome where these are the people that do show up for their appointments. We only have 1 patient who has to wait, but then he can be seen in the next slot. That's sort of the lucky case. We can also have an unlucky case where we have the same overbooking schedule. These are the patients that show up, and then now we need to use overtime, and this is not a very effective way to mitigate for no-shows. What we found was overbooking is still a good concept. We don't want to sort of completely throw it away. What we want to do is overbook more smart. And so what we want to do is use individual patient no-shows probability in order to overbook. So let's not say there's a sort of general population of tendency to no-show. Everybody, based upon their personal demographics or their appointment information, has an individual probability of show. Okay, so let's say we decide to move forward with that concept, and let's say we have 5 patients here. I'll be using this concept of these 5 patients throughout this presentation. So let's just lay it out. We have A and B, who have a probability of no-show similar there in one group, and C, D, and E are in the next group. A and B are at a lower risk of no-show, and C, D, and E are more likely to no-show. So even though they're scheduled for an appointment, it's more likely that they won't show up. So let's say we have these 5 patients and we want to schedule them in these 4 appointments, which means in order to get all of them into the system, we will have to overbook. Now, what we can do instead of just using the population show rate is we can use some sort of machine learning algorithm to predict the show probability of each of these patients. Let's say we do that. A and B, their probability of show is 85% and 75%, and C, D, and E is 70, 70, and 60 respectively. So you have like a high show group and a low show group. What we can do is we can take these probabilities that are based upon patient demographics, patient no-show history, appointment information, and we can input them into a schedule optimization. The traditional schedule optimization says, let's minimize cost, which is a function of the patient's waiting time, and the provider's overtime and idle time. So we have our probabilities we get from a machine learning algorithm, we input them into our schedule optimization, and we can prove that this here is the optimal schedule. Here we can see that we have the person with the highest show probability first, the next highest show probability here is in B, and then it goes sort of backwards down, C, and then D and E. Note that the low probability group are clumped here in the middle, in the overbooked slot, and the slot right after. This is the optimal schedule for this group of patients. So we're getting a better schedule because we're using no-show probability, but let's see also the worst case scenario if all of them show up. All right, we got a little animation here with a little doctor. All of them show up. So the doctor comes up, sees patient A, there's no way for patient A, had the highest probability of show. That's good. The doctor's not idle, patient doesn't wait. Go to slot 2, there's only one slot, I have to move everybody down. Patient D doesn't wait. Patient E does because they actually showed up on time on slot 2. Patient C now waits. Patient B waits, and now we have clinic overtime. Now, this is a traditional objective function where we have function of waiting time and idle time and overtime. So we want to minimize this cost. So we have individual waiting time for each patient times some parameter CW, and the idle time and the overtime of the doctor times our parameters CI and CO. So this is a traditional function that we in literature and in practice say this will get us to a solution that minimizes the cost of the clinic, understanding that patients may no-show. Okay. What we find, and this is sort of, I guess, the banner message of our paper, is that if we use this traditional objective function to schedule patients, patients with the higher risk of no-show will wait significantly longer in the system. When we say significantly, we mean statistically significantly longer in the system. So that's a very important point. Right now, we're not necessarily talking about race. We're just saying, in general, patients with the higher risk of no-show, so in our case, D, D, and E, are going to wait longer. But how does this then relate to racial disparity? How did we get from that concept to racial disparity in wait times? Well, using the data that we had, and probably in many circumstances, we find that no-show probability is correlated with race and socioeconomic status. In a 2018 paper, Donch et al., he finds, and I quote, minority groups were consistently associated with increased no-show, but the concept of minority varies based upon the application. In our case, we had data for white, Black, Asian, and other patients. We find that Black patients, their show rate was 66.1. White patients, their show rate was 78.1. And so when we talked about minority, in our case, it was sort of the Black patients were the minority, and they had a higher risk of no-show. We talked about on the prior slide that we could see, based upon our little toy example, that patients who are more likely to no-show are found to wait longer. And then we find in our case that those patients are the Black patients. And we have to say, okay, if we don't explicitly account for that sort of difference in show probability in our schedule optimization, it's going to lead to racial disparities. Now, some of you may be thinking, okay, well, people don't show up for their appointments. Maybe they should be scheduled in a way that is better for the clinic because they're not showing up. And we've received that question in appropriate ways and inappropriate ways when trying to publish this paper. And to that, what we have sort of come up with is, if we're finding that the no-show probability is correlated with race and socioeconomic factors, then there's sort of like social determinants of health that are potentially making certain people not show up for their appointments. We're not talking about people who say, oh, I knew I had an appointment today, I had the means to get there, and I just didn't go. We're talking about people who maybe couldn't get childcare, people who the bus was late and they couldn't get there, their car broke down, they couldn't get time off of work. There are things here that are beyond the patient's control that are affecting their ability to show up for their doctor's appointments. And since access to healthcare is a basic right, we needed to make sure that, when we're building these, fancy models, that we understand that the data that we're using to build the models could have some sort of bias related to it. And we need to understand that and account for it. So we've made the argument that we have this great objective function we can use to schedule patients, but that will lead to disparity for the people who have the highest probability of no-show. So let me sort of prove it to you. That traditional objective function leads to sort of this static scheduling concept where you can define, if you know the parameters of your model, like CW, CI, CO, the basic structure of a schedule. So it says to us that there are this concept of what we call P slots. P slots are the slots in the beginning of the day. Let me see if it's working. Yes, perfect. The slots in the beginning of the day, such that there's no possibility that that patient is going to wait because there's going to be no overbooking. But these are reserved for patients with a very high show probability. For reasonable parameters of the system, the show probability is about 83%. So if you have a show probability greater than that, you're sort of guaranteed to get into these first slots of the day where you're guaranteed not to wait. And that's actually good. We put them there so the doctor's not idle because that's part of our objective function. Yeah.
So this is not based on any history of that particular person. It's based on characteristics of the person.
What is not?
So the show probability is based on, I think I heard you say, based on the characteristics of the person, not the history of the person.
Oh, the history of the person is also part of that. So it's the patient demographics, their no-show history, and then the appointment information. One could argue that each of the past histories also sort of has demographics baked into it. But yes, their no-show history also is part of it. Mm-hmm.
Thanks.
Oh, it is working. Great, I can move around. So we have these P slots that are guaranteed to patients with a high show probability, which they'll get if they, in the past, had shown up for the majority of their appointments. And then we have this concept of vertical and horizontal segment. A vertical segment is an overbooked slot. So if you have more than one patient in a slot, it's a vertical segment. A horizontal segment is sort of what comes after a vertical segment. There may be a schedule structure such that you have two overbooked segments next to each other. But in this case, we have a graphic where we have an overbooked segment, a Z slot, which is the appointment right after, and then H. Why does this matter? It matters because this is sort of what happens with our little schedule. We have a P slot, they have an 85% show probability, they're above the threshold, they get put there. Then essentially the person with the next highest show probability gets put here, 65%, 70, and then the two lowest get put into our overbooked slot. Now, this structure is poor for these people in this OB and Z slot, and we'll see how that sort of leads to issues. So in the paper, all of these propositions are proven and written out, but I wanted to sort of go over with you sort of broadly the propositions in the paper and how they lead us to sort of understanding the concept of racial disparity. So, as I said before, P slots are assigned to the patients with the highest show probability. If we know that the patients with the higher risk of no-show, so lower show probability, are the Black patients, then there's a low probability that Black patients will get P slots. P slots are commonly present because sort of, again, this threshold of 83% seems high, but it's not too unattainable if you have people who show for their appointment. The Harias and Pinedo, they are the ones that came up with this concept of the vertical and horizontal segments, and you can prove that OB slots have the lowest show probability, and it increases up to HN, as we saw before. And if we relate those placements to waiting time, which is sort of the point of our paper, where we calculate the conditional waiting time, which is the waiting time for a patient conditional on them showing up for their appointment, we can prove that patients in OB and Z have the longest wait, and then patient in HN has the shortest wait. And this makes semi-intuitive sense, right? The person farthest away from the overbooked slot has sort of the most time for the issues in the system to dissipate, right? So even if all three of these patients show up, then two of them are definitely going to wait. But if two of these patients don't show up, then HN is sort of cleared. They're going to be seen on time. So HN has the shortest wait in expectation, and the patients in OB and Z have the longest wait. But if you remember from our toy schedule, those are the patients in the group with the highest risk of no-show. So within each vertical segment with the patients with the highest risk of no-show, patients with a lower show probability have a longer CWT or conditional waiting time. And again, so patients in OB have a longer conditional wait time if they have a very low show probability. So it's sort of like compounding on top of each other. If you're likely to show, you're in a great spot. Or you're in a spot where if there's overbooking, there'll be time to dissipate it. If you have a low show probability, you're sort of packed into this middle of the schedule where there's a lot that can happen to make it so that you wait longer in the clinic. Are there any questions? How would I know if there was questions on Zoom?
I have a question.
Oh.
For this particular model, how well this perform actually on the newly established medical practices, where they have no prior knowledge on their patients?
The ethical practices?
He
Yes.
means, like, suppose you just start, like, a person just joins your practice.
I'm not sure exactly how to answer that question, but if there was a patient that just joined the practice and then there was sort of no information on them, the assumption would be that you could still use their demographic information to generate a no-show probability. Like they wouldn't have a no-show history, so that part would sort of go to zero. But there's a slide soon, this one, where we're going to talk about appointment level characteristics and sort of the factors that we use to calculate no-show probability. And you'll see that even if it's a new patient, we'll get to the point that we're able to calculate a show probability. Does that answer your question?
I was more curious about the racial profile for the incoming patients. Given they are new to the system, are they going to be assigned a label that is corresponding to their background, regardless of their new history of show or no show?
Yes. So the clinic will ask them about, well, there are some clinics that ask patients their racial history, and some of them just assign it based upon looking at them.
Observation.
Yes, they would still be able to get that information from the new patients. Mm-hmm. It's sort of a pre-screening concept before they came in for their first appointment.
I see. Thank you.
Okay. Yes.
So my next question is about people abandoning. Is it possible that this proposition would still hold even if you have people that leave after some time?
I do not know. That is a very interesting question, one that would, I think, need to be answered having this set up as a queuing model, which would, I think, be very interesting. What we're finding in some of our research about this concept of race and socioeconomic status being related to no-show probability is that there is studies about it there being a negative feedback loop. So I come, I wait for forever. Now I don't show up for my next appointment because I feel as if you don't care about me as a patient. Or I feel you seem so busy, doctor, I don't really need to show up for my appointment. If I feel better, then I'm not going to call you. So there is, people who have negative experiences, it increases their future probability of no-show, and then it's sort of a negative feedback loop. So I assume it would be something like that, but we haven't studied it. Okay, so this has been sort of explaining the concept of our problem in our model with a toy example, but we did have real world data and we did some computational experiments, and I'd like to now talk about those.
Quick question.
Yes.
Your setup, I understand why, assumes that the clinic gets to choose slots for people.
Mm-hmm.
But in some practices, let's just say like ZocDoc
Mm-hmm.
or something like that, you may be able to sort of choose yourself. And so I think there's interesting work where you could see like a mix of the clinic choosing versus the patient being able to choose for themselves.
Yes, so, and I guess I have a question back for you. On ZocDoc, the clinic can choose what appointments to show each patient.
Yeah.
Right?
Yeah.
So there's still a clinic choice there. You could still be, can I get there? Yeah. in this sort of low probability category, and they're not going to show you this one. They're only going to show you these two. And then you can choose between those two. And they're like, okay, fine.
The question is if that was ZocDoc, but how would I be able to get the P slots if like the clinic doesn't show them to me?
Yeah, you wouldn't be able to unless the clinic has designated you worthy based upon your probability of show. Okay, so our simulation, our computational experiments, were based upon approximately 40,000 appointments and 13,000 patients in a local healthcare outpatient clinic. And we have here the relative frequency and show rate for each of our racial groups. We have white, Black, Asian, and other. And in order to sort of group patients into two groups, because that's what we did for our experiment, we have Black patients as group 1, who have the lowest probability of show or highest risk of no show. And then we group white, Asian, and other into group 2. So group 2 is the group that is more likely to show for their appointments. So we first, sort of from a slide from before, we see that we have these patients, they're going to request appointments, but one of the first steps is for us to predict their probability of no-show. So what about them in the data set do we have in order to predict that no-show probability? Well, we have appointment level characteristics. Again, so this would be for the data we have in our data set, it would be for already completed appointments. But even if you were a new patient, you were calling in, you would request an appointment and they would know what day and time and day of the week that appointment would be in. And so you can use those appointment level characteristics to predict their probability of no-show. We have several patient level features, and you'll see why sort of this was important in the next couple slides. But we try to break them out into what could be labeled as a race or a socioeconomic factor, and what would just be potentially just a patient level demographic factor. So the factors that we've listed here as socioeconomic are the patient's marital status, employment status, employer, city name, zip code, county name, preferred language, distance between their home and the clinic, and dummies for the patient's insurance. And we did this based upon sort of other papers that have studied the concept of socioeconomic status and variables that have been used to study socioeconomic status. We also have their patient's past number of no-shows, which could be considered socioeconomic because sort of if they didn't show up in the past, it could be because of those features, but we left it out as a basic patient level feature. Their past no-show rate, their age, number of past appointments, their average lateness, and their time in the system. So we have all of this data. Some of it we would have for new patients, some of it we wouldn't, but we can use it to put into a predictive model to predict our dependent variable, whether or not the patient will show or no show. So we have our data, we split it into 80% training, 20% test. We use 5 different classifiers and executed 10-fold cross-validation on the training set. We choose the preferred classifier based upon the classifier with the smallest Breyer score. There is an option to choose the model that has the highest area under the ROC curve, but we found in a prior paper that using smallest Breyer score reflects scheduling performance better. So we predict the show probability of every appointment of the test set, and then we use that in order to schedule. So classification performance. How did we do with the classifiers that we chose? Well, we had 5 classifiers: random forest, Gaussian naive Bayes, lasso plus logistic regression, Eta boost, and multi-layer perceptron. We have the AUCs and the Breyer scores listed here because we want the lowest Breyer score. The lasso plus logistic regression is what we chose. So what we did every time that we needed a probability is we did feature selection on the current training data set using lasso regression, and then logistic regression on the reduced feature set. So we did this as part of our simulation, and we found that there wasn't too much overfitting in our data, which is very important. So what's our simulation? For 5,000 times, we sampled N appointment requests from the test set. So we have N patients who are going to be needed to be scheduled in our scheduling system. We use our chosen classifier, in this case, Lasso plus logistic regression, to predict the patient's show probability and use that probability to schedule those patients into F appointment slots, where F is less than N, such that we need to overbook. And then, since it's a test set, we know the actual outcome, whether the patient showed or no showed. We use that as our outcome measure to measure schedule cost, and then the waiting times of Black patients and non-Black patients, where again, Black patients are G1.
So in your data set, nobody left?
I don't know if that's recorded.
I see.
So
Seems that it could be truncated.
it could. I guess if we had the time that they were in the system, we could look at that.
Yeah,
I guess I don't think we
it
even.
would be longer if they with their patients.
Yes,
Patients.
I will write that down at some point. But yes, that's not something that we even thought about, but it's something interesting to look at, because there could have been people who showed up and then just were in the system for a very short time, and it could be because they abandoned. Okay, so
I mean, in the specific clinic you got the data from, I'm pretty sure they don't measure whether, like, what time you leave.
I don't think so, but they can as part of the study. But I don't not like traditional. No, they don't measure what time people leave.
I have a question.
Oh yes.
So far, you built a model based on the general qualifications of a person, the race, background, the distance, and all other metrics that he just displayed. And
Right.
it gave a label to a person of this particular qualifications will have a assigned probability of some number. And and basically you run the analysis, and the queuing will be based on that, or the reservation will be based on that. But do you have a feedback loop where the individual behavior onward can update the probability that actually assigned to that person qualifications? Let's say person have same qualifications, but happen to be individually punctuate, showing up for everyone, every appointment. Well, that would be updated at some point?
Yes. So if one patient has multiple appointments in the data set, we can predict their future no-show probabilities for the future appointments based on what they did in the past. And how far did I go? Oh goodness. Okay. I won't go back all the way to the appointment level features, but the variables that were associated with like their past no-show history, obviously, if they showed up in the past, they had a higher show probability. So if yes, you could maybe say on average, Black people are more likely to no-show. But if there was a person who their race was Black and in their past they missed no appointment, they would still, based upon that, be able to have a higher probability of show.
Thank you.
Yeah. Okay. Good. So here we have sort of the beginning of our results. And we refer to this says all features state-of-the-art model underneath the little screen. And we call it TOF2. But what we need to know here is this. In order to generate the schedule, we use this traditional optimization function, which we went over before, and the Lasso plus logistic regression with all available features to generate the no-show probability. If we do that, this is like a state-of-the-art system. We've got all features, the standard scheduling optimization. This is what we find. The results are broken down based upon 4 sort of clinic sizes and patient that we want to schedule. So N is the number of patients, F is the number of slots. So we go from smallest to largest in terms of clinic size. For each of these, we measure the average overtime of the provider. the average idle time of the provider, the Black patient's weight, the non-Black patient's weight, the weight greater than 30 minutes for percentage Black, percentage non-Black. So in this case, 38% of the Black patients waited longer than 30 minutes, and 29% of the non-Black patients waited longer than 30 minutes. Then we have the racial disparity measured as the difference in wait times between the two groups, and the cost versus TOF2. Obviously, it's 0 because this is TOF2, but this is sort of what we call the status quo that we will measure everything against. So we can see that it's going to have the best cost because that's what we've decided as sort of our measure of the scheduling cost is the best, but there's very high racial disparity, about 33%. So how can we just remove racial disparity? What are the different ways that we can affect this model and sort of make it so there is fairness in the scheduling model? Well, one thing we can do is we can make the show probabilities less correlated with race, which is could potentially work. Let's maybe remove those socioeconomic factors. Or we can include fairness in the objective. So we're going to go over 3 to 5 methodologies that we went through to try to understand how we can remove this disparity. The first being, let's just not use any machine learning. That's the problem anyway. We moved from average population show rate to individual show probabilities because we felt like we could get a better model, a better system, but we may have broken the system by doing that because we have data that's racially biased. Now, if you have a clinic that does not have data that's racially biased or gender biased or sexual orientation biased, then that's great. I would argue that that may not occur in reality, but we said, okay, we know that the data is biased, and so let's just remove all machine learning. The results for that model are here in this column. We call it TOF0. Oh, oh goodness, there we go, this one. We have our optimization model, which is the same as before, but we just assign all the patients the average probability of show. And what we see here is there is less racial disparity across all of these 4 schedules, but we're not getting a very good cost because we're ignoring the rich data that we have that can help us in a way to get to a better solution. So it's our argument that TOF0, no predictive model, is not the best way to move forward. All right, so we've got sort of 2 ends of the spectrum here. Let's see if we can get someplace better in the middle. All right, so let's just remove those factors that we say are related to socioeconomic status. There's still other rich information that we had on that slide. There's still maybe 15 other factors we can use. Let's just remove the ones that we believe are related to socioeconomic status and see where we get. And what we find is that everything degrades in this case. We're not able to predict show probability as well, and the schedule quality decreases. And there's still racial disparity. So, you know, we have 3 options here. Use the traditional objective function, and then use what I was thinking of calling like a lot of features, a little bit of features, or no features. And none of them are really getting us to where we want. When we sort of try to bridge the gap and sort of cherry pick which features may be related to race or may not be, we have bad racial disparity and bad cost. Sort of, we're not where we want to be. So we've talked about adjusting this machine learning algorithm, which there could be other ways that we did not present here or think of that you could do it. I know there's another academic, Zaid Obermeyer, who has a whole handbook on how you can sort of reduce algorithmic bias and has ideas about like how you can adjust the data and weight the data in order to get there. But what we thought of was, you know, we have this rich data, this is a social problem, and we want to, in other projects, think of the ways that we can gain more trust with our patients, understand our patients better in order to make sure that there is less racial bias in our data. But we know it's there, so why don't we just account for it directly when we're optimizing? We've identified it. We will try to do better in the future. But for now, let's just account for it when we're optimizing. So the traditional objective function minimizes all patients' wait times. What we propose is what we very explicitly call a race-aware schedule optimization. In this race-aware schedule optimization, you minimize the waiting time of the racial group expected to wait longer. So in essence, you say, hey, let me sort of get equality among waiting times for the groups. I got my 5-minute notification, so I'm going to speed through some of this a little bit quickly. But then we said, we had some people push back very hard on the fact that we're using race explicitly. So we said, okay, let's just use a race unaware, where we minimize the waiting time of the patient expected to wait longest. And then we also decided to think of a way where let's split the groups, not by race, but high no-show, low no-show, and see where we get. But in general, the UOF, as we call it, the unbiased objective function, explicitly breaks people into two groups and says, let us have equality among the groups. The race-aware objective, the two groups are split upon race, and unaware, we're split based upon, again, minimizing waiting time among each individual patient that's expected to wait longest, or sort of splitting people based on no-show and show. Now, how did we solve this? Well, we can prove that there exists a schedule with no empty slots, and we can characterize a segment, which allows us to solve this through complete enumeration, because yes, the possible schedules increases exponentially, but if you can, based upon optimality conditions, remove a whole bunch of the schedules, we can do this by complete enumeration. So this chart has all of our sort of possible fixes in it. We already went through TOF 0, 1, and 2, which is traditional objective function with a little, or no features. And here we have the UOF, the unbiased objective function, that is race-aware, sort of minimizing the maximum of an individual patient, or this concept of let's split people into high no-show and low no-show groups. What we find here, there's only one on here that gets us very close to the cost of the state-of-the-art system and results in minimal racial disparity. And that's the one where we take race explicitly into account. So it is possible to achieve both fairness and schedule efficiency, but it doesn't come from us sort of identifying that there's a problem with race and then saying, well, let's try to just like fix these other things around it. It comes from us identifying the issue with race and then explicitly adjusting for that in our objective function. Now,
a question from David Goldberg.
Oh, yes.
Yeah, so maybe you're about to address this now, I sense, but I was just going to ask if the intuition behind the objective is that, do you end up with a schedule where the different kind of groups of people are themselves totally sorted out? Like,
yeah, okay, perfect.
Everyone from this group comes first, and within that group, it's sorted this way, and then everyone from the next group, or is intuitively more what's going on that like, your answer is almost the reverse of the original system where it's just people are sorted the other way by probability of no-show, just like irregardless of what group you're in. Namely, if you're a very high no-show probability, but you're not from the group that's kind of maybe being most advantaged currently, you're still going to come first, even though you were from a group that is really treated fine because your no-show probability so high. Like, how should we think about that, I guess?
Yeah, so it's a little, you have sort of two main things. It's like a little column A, little column B, right? We still need to do a full research sort of to answer your question on sort of all of the schedule. So the thing about doing this statically is we can generate all possible schedules and we can study exactly how each of them changes. This is on average what we found, how the schedule changed. So again, we're comparing this to TOF2. Each of these numbers is first the percentage black in a specific slot, and the next is the percentage non-black. Remember, O, B, and D are sort of the middle cluster of the schedule. P are the ones that are guaranteed not to show, and H are the ones that are benefiting from being able to be farther away from O, B, and D. Now, we find
So-
here,
Sorry, maybe just following up, just so that I make sure I understand the picture there. So is that picture saying that indeed the groups themselves are totally sorted? Like everyone from the first group comes where there's some order on them, and then everyone from the next group comes. Is that what that's what the picture looks like? Is that what it's saying?
not necessarily. So there could be both Black and non-Black patients in this segment. Is that what you mean by groups?
I think so. What does OB mean? Maybe I
It
missed.
means you're in an overbooked slot. So
Oh.
we have two groups, like Black patients and non-Black patients. And so P just means you're not overbooked at all and there's no chance of you waiting. OB means you're in an overbooked slot. Z means you're right after that. And H means you're sort of after the
I see.
overbooked slot.
I see.
happens.
Okay, sorry. I didn't understand. Okay.
So what we find is there is a switch. I think that was one of the things you said. Does it just switch? And the answer is sort of yes. So here we had 10% Black and 6% non-Black in these OB and Z slots, and that does switch where we have UFR. In the H slots, it's a little bit, again, more Black people are being just put close to there in the HN slots, but we find that it's almost exactly the same percentage according to the P slots. So the P slots are still reserved for those people who are going to come, and that's fine. There's just more of a mix-up in the middle of the schedule. And to compare it to our little toy problem, this is what we were working with before, but now with our race aware objective, these two Black patients are actually scheduled in the first slot of the day. If you go back to scheduling theory from like 1952, barely, that was his solution. So before we had any of this, he said, overbook the first slot of the day, the doctor's guaranteed not to be idle. And that's sort of what we come back to. And answer your question a little more, David, you notice here there's a little more, a clump of the groups here, but we see it just so you alternate now probabilities throughout the day. Yes, I get 1 minute. I'm done.
Okay. So then I have a question.
Yes,
It seems to me that a lot of this is dictated by the cost function.
yes.
How much it costs to go into overtime, et cetera.
Yes.
What if I just ramped up the cost to go to overtime? Would that change the?
Oh, yes. Oh, yes, that changes it a lot. And so we use sort of, in the literature, sort of standard CW, CI, and CO. CO is typically 1.5 times idle time. So essentially the doctor's time is sort of 50% more valuable in overtime. Yes, there are other papers in literature where you can find if you ramp it up to 2 to 3, you make completely different scheduling decisions. Another thing that sort of is the waiting time of the patient. If we care a lot about the patient's waiting, so let's say we have hour-long appointments, we can't have patients wait, the higher CW goes, it does affect our scheduling decisions. But you can still, within sort of the realm of each parameter values, have a better schedule.
I still see the same racial disparities.
Yes.
Okay.
Yeah, in the paper, we compared like CW is 0.3, 0.5, 0.7. Yeah. Okay, so one question that we get is this ethical? And aren't you hurting the good patients? And I think my answer to that is that whenever we're talking about bias and disparity in race or sexual orientation or anything, and as researchers, we do measure the difference from status quo, because in terms of being able to measure statistical difference, that's very convenient. But I do think that if you're a clinic, you use the system and you understand that there's racial disparity, it's not about change from status quo, it's about we need to institute a new system that works for everyone. And we've had some reviewers say inappropriately and appropriately, sort of had you defend sort of moving some of the patients who were going to show sort of into worse spots. And I would just say, we're talking about not moving from a bad system, we're starting with a new equitable system. And sort of that's our goal. And what's been very nice is sort of investigating this problem has led McKinley and I into sort of a whole research stream on this concept. And so I can talk more about this with people later. I don't want to take up people's time. I know I'm out of time, but thank you so much for your attention. Are there any more questions? Any more questions on Zoom? Okay. Oh, yes.
I was wondering, it seems in your model you assume you just predict like a single probability. I wonder if you've considered instead predicting, say, like a confidence interval for the true probability instead, and could you still solve the scheduling problem in that case?
I don't know the answer to that question. I will answer you this question though. In which one? Oh, this one, right here. We talk about appointment delay. So not necessarily you're waiting in the clinic, but you're waiting like days. And in that case, we do sort of have an array of no-show probabilities where we say, you know, if you like make someone wait longer, they're less likely to show. And how does that affect someone's, you know, effect on the system and how they wait for the appointment? The confidence interval thing is a very interesting question. And we could like maybe think of like the overlaps and how that necessarily affects the outcome, but we have not thought of that.
She used Gaussian processes. She could give a confidence interval, but she didn't do that.
Well, maybe we could collaborate and do that wrong. Yeah,
sure.
there it is. Mm-hmm. Are there any other questions?
I actually had another question
Okay.
too. Could you go back like 2 slides, I think? The one before this with like the big table. What does the percent black versus percent non-black mean? Because I kind of feel like it should add up to 100%. So.
Oh. Should it add up? I don't think so. Hold on, let me see how I can. Percentage of black versus percentage of non-black scheduled in undesirable appointment slots. So we have, let's say this one. This is OB slots. What percentage of black people were scheduled in overbooked slots? 71%.
The column.
And what percentage of?
Oh, okay.
So like the 66, 17, 17,
Okay,
0, 0, 100, 259, blah, blah, 100. So each column adds up to 100.
14, 24, 27, 100. So yes, something on here does, just not these.
The column.
Does that answer your question?
Yeah.
Does that help?
Makes sense.
Okay. And this was very interesting for us. I mean, we do want to look into this more, similar to David's question, because you would think that it would be just only the overbooked slots, like, oh, let's just overbook someone more. But there's a little more nuance to the solution, which I think is good. And we get equality of wait times and a still efficient schedule. All right, thank you very much, everyone.